Good afternoon to all the faculty members. A gentle reminder that we would be starting the session at sharp 5 p.m. So kindly tell your faculty members to join in quick. So a very good afternoon, everyone. A warm welcome to all the directors, HODs, professors, and faculty members who have joined in here us for today. On behalf of XLR, I sincerely thank you all for taking your time to be a part of this faculty development program on quantum computing. So before we begin, let me give you a quick introduction to XLR. XLR was founded by an IIM ISB alumni in the year 2013, and it has 8 branches in 8 cities with its headquarters in Houston, USA. So far, XLR has trained almost 8 lakh plus students and professionals across various domains, catering to individuals, institutions, and industries. So, few of our premium associations include iHub Divya Sampark, Naipunyam Skillati, APSHE, TAS, BFSI, NASCOM Future Skill Prime, and many more. With over a decade of excellence in training, we have conducted 1,000 plus webinars, offered 30 plus technical courses, collaborated with 2,000 plus academic partners, and worked with 5,000 plus placement partners. We have trained almost 80,000 plus faculty through the faculty development program and 8 lakh plus students through the student development program. Till date, we have about 8 lakh 28,853 students participating and 76,577 faculties participating in our everyday learning program. For today's faculty development program on quantum computing, we have registrations from various states with a total of 2006 registration, with Andhra Pradesh having the highest with 792, followed by Telangana with 438 registration. We also have faculties participating from different streams such as engineering, degree, MBA, and also MCA. Our Everyday Learning initiative, which focuses on providing application and industry-oriented learning on trending technologies for free from industry experts with in-depth knowledge on the subjects. The goal is to provide hands-on learning experience, help students and faculty with real-world application, support institutions in meeting NAC and NBA requirements. So you can find the registration link in the chat box also. The learner can click on it to register, or they may also visit the Excella website to complete their registration. Upon successful completion of the program, participants will receive a participation certificate. Additionally, we also collaborate with colleges by signing MOUs to conduct and collaborate for the SDPs and the FDPs, along with placement readiness drive to support students in their career development. Through the everyday learning programs, a learner or a participant benefit from 30 plus hours of professional training, assignment and assessments, real world industry use cases, placement preparation sessions, coding challenges and campus recruitment training, a lifetime LMS access, and certificates for participation. So this is how our LMS dashboard looks like. The students or the faculties who have joined in here can log in using the username and the password that they have received through their email after registration. And then they can access the course they have enrolled in. They can also view the courses they have registered for in the past. So far, we have conducted almost 73 student development programs and around 2,000 plus colleges have been actively participating. We have delivered around 2,300 plus hours with a total of 8 lakh students having their enrollments. And these are the few common programs among the student development program. We have advanced Excel, Salesforce, tracking code interviews, and full stack development. For the faculty development program, we have conducted almost 50 plus with 600 plus hours delivered and 2,16,927 enrollment of faculties and 2,000 plus colleges who are actively participating in a faculty development program. And among the faculty development program, these are the few programs which are common. We have digital marketing, data analytics, deep learning and AI. So this is how our student and faculty certificates looks like. These certificate will be given to the learner after they register for the program and attend for the learners to mark their attendance in each session so as to be eligible to receive the certificate upon completion. So these are few of our recent engagement like IIT Roorkee, where we have conducted training on data analytics using Minitab. This was at BITS Pilani campus in Hyderabad, and the program for the students were conducted on Power BI and machine learning. So this was a student initiative where the student themselves had approached Excella to conduct the programs. We also had a skill up program for the final years, which was a 240 plus hours of campus recruitment training with placement assistance that started from Jan 2024 to April 2024 and had covered coding skills, quantitative aptitude, logical reasoning, verbal ability, soft skills, resume and LinkedIn profile building. There was also a group discussion and the personal interview provided at the end of the training. So this program has benefited thousands of students with placement assistance. This is a participation certificate that was provided to the students after the completion of the Skill Up program. And this was issued by IHUB Divya Sampar, which is a joint initiative of IIT Roorkee and the Government of India's Department of Science and Technology, where out of 50,000 students, only 5,200 students were eligible for the certificate that was given based on their attendance and assignment. These are the few newspaper snippets covering the Skill Up program. Where around 10,150 engineering students had attended the online program. March, this was in April, and this was in May. It's my pleasure guest for the day. We are honored to have a distinguished academician with us who bring us decades of experience, research excellence, and also contribution to education and innovation. First, we have Dr. Monica Bhagawat, Professor and Head, Department of Electronics and Computer Science, Pillai College of Engineering, New Panvel. Ma'am has 27 years of academic excellence as Professor and Head from the Department of Electronics and Computer Science and as an IQAC Coordinator at Pillai College of Engineering, New Panvel, Mumbai. She has also been a senior member of IEEE with a BE from Government Engineering College, Jabalpur, and MTech with a gold medalist and PhD from VJTI, Mumbai. She has accomplished researcher and mentor with 20 plus publications in reputed journals and conferences, guidance to 11 postgraduate and 35 plus undergraduate students, and currently supervising 3 PhD scholars. Her research expertise in artificial intelligence, deep learning, smart grids, nonlinear control systems, and power electronics with a strong focus on innovation, research, and academic excellence. Dr. Monica, ma'am, we would like to hear a few words from your side.
Thank you, ma'am. I hope I'm audible.
Yes, ma'am, you're audible.
Yeah. So, a very good afternoon to all the distinguished dignitaries, resource persons, and faculty members and participants. It gives me immense pleasure to welcome you all to this 5-day faculty development program on quantum computing, which is jointly organized by XLR and Pillai College of Engineering under our MOU with XLR. So, firstly, I would like to brief you all about our institution, that is Pillai College of Engineering. PC, it is an autonomous institution situated at New Panvel, Navi Mumbai, Maharashtra. And we are our establishment year goes to 1999. And since our establishment, we have been consistently stood as one of India's premier engineering institutions. With that, our commitment to academic excellence, innovation, and research, it is reflected in our A+ grade by NAC and NBA accreditations. Building on the autonomous status granted by the UGC in 2021, I'm feeling very proud to share a historic milestone. That is, from this year onwards, the Pillai College has been conferred state private university status by the government of Maharashtra, and making us one of the first state private university in Navi Mumbai. So this achievement reaffirms our deep commitment to excellence in higher education. Now, at PCE, we firmly believe in preparing both our students and faculty for the technologies that will shape their future. So, as part of this progressive vision, we introduced an institute level specialization in quantum computing and technologies in last academic year to give our students early exposure to this transformative field. Now, this faculty development program is again an extension of this initiative, and it is aimed specifically at empowering our faculty members with the knowledge and skills needed to effectively teach, mentor, and contribute to research in this emerging domain. Now, quantum computing, as we all know, it is one of the most revolutionary technological advancement of this century. And unlike classical computers, quantum computers utilize qubits, leveraging the principles of superposition and entanglement to solve complex problems exponentially faster, which is the advantage of quantum computers over classical computers. So this application of this technology is very vast and I would say disruptive, which spans from cryptography, cybersecurity, AI, drug delivery or drug discovery, material science, and financial modeling. So across the globe, governments and technical giants are investing heavily in this particular domain. And most of us might be knowing that Government of India is also funding heavily for the development of the labs related to quantum computing, and through their mission, that is National Quantum Mission. So as educator, it is crucial that we stay ahead of these technological advancement, and we must enrich our curriculum and prepare our students for the careers of tomorrow. So programs from XLR like faculty development program and the student development program, which are offered by the XLR, are very vital to bridge this gap between the academic learning and industry expectations, while also fostering interdisciplinary research and innovation. So I'm confident that over the next 5 days, this program will provide all the participants with a strong foundational understanding of quantum computing, and by covering its core principles, programming techniques, practical applications, and emerging research trends. And I hope the knowledge and skill gained through these sessions will enrich your teaching, inspire innovative research, and open new avenues for academic and industry collaborations. Once again, I extend my sincere gratitude to XLR for partnering with us and bringing together such experienced expertise to share their practical insights. And with these words, I once again extend a very warm welcome to everyone present here. And I wish all the participants an engaging, enriching, and rewarding learning experience. I wish this FDP a great success. Thank you and happy learning.
Thank you so much, ma'am, for sharing your kind words. It was a pleasure having you with us today. Thank you so much. Next, we have our subject matter expert for the day, Mr. Keshan Srivastava, who is an AI, ML, and quantum computing professional with expertise in machine learning, deep learning, generative AI, and quantum computing and Python. He's an academic and researcher with an MTech in AI/ML, rank holder experienced in teaching, mentoring, and developing innovative AI and quantum computing solutions. He's also been an award-winning quantum computing educator recognized through global certifications, hackathons, and workshops in AI and quantum technologies. Sir, we would like to hear a few words from your end. Yes, sir, but your voice is a little feeble, so.
Okay. Am I audible now? Is
Yes,
it okay?
sir. Yes.
Okay. Thank you, Sheetal ma'am, for this lovely introduction. And yeah, so ma'am has already discussed. Monica ma'am has already briefed very beautifully about the idea of quantum computing. And uh, over the next course of 5 days, we will be focusing on various ideas related to quantum computing, uh, specifically focusing on the foundations from ground up. That what exactly goes in the understanding of the idea of quantum computing. Why exactly we are like moving towards this idea of quantum computing? That's the very fundamental idea, and this gives rise to the inner workings or inner understandings of how the everything runs. So the idea of foundational understanding, we will move towards start with that and understand the basic ideas around there. That is the agenda for day one, that is today. uh, Moving on towards day two, we will be focusing on uh, the inner workings, that how to build or run circuits, quantum circuits, just like we do in classical computing. We build some circuits, and based on that, we have made we can say a kind of a advantage in many fields, and many emerging areas are also coming up with the ideas of generative AI, agentic AI, and much more than that. Then third day is like as in general tendency, it is like a moving day, and this is where we will be focusing on the quantum advantage that comes up uh, in practical form, and through different quantum algorithms, we'll see what are the changes that we see from perspective of classical algorithms. And day four, we will be moving towards one specific understanding of that how quantum computing can be infused with the idea of artificial intelligence and machine learning. So we'll specifically focus on the idea of quantum machine learning, and see the variational and hybrid methods. And on the lastly, we will be focusing towards the idea that what exactly is the current scenario, because currently we are lacking in the hardware part, that is quantum hardware. This is where many problems are there. What are the applications of quantum computing and associated areas around it, and how this can be integrated? The idea of quantum computing can be integrated yeah, as a classroom course, in classroom teaching. So we'll be focusing on this particular roadmap. Now, the idea of infusing all of these is important, and as we understand that faculties are the multipliers of, we can say, in the terms of learning patterns. So as we connect with an educator, the educator is possibly going to reach hundreds of students. That particular educator will be imparting their learnings. So FDPs are a great way to bridge this gap between what's exactly taught and what's needed. And uh, a very I want to thank XLR for asking me to be the resource person for this FDP, and the focus they come up with, that we do not need just the exposure to new tools, but we also need the resources to how to teach them. So that is a very good practice that XLR is doing. And the idea of AI and quantum computing, data science, and many emerging fields, whether it is cryptography or, as just I earlier said, generative AI or agentic AI, we are trying to collaborate. We are trying to connect all these technologies in such packets that the gap between the research labs and the classroom, it you can say compresses. And the curricula that is we have been like teaching, it must evolve now very rapidly in years, not just in decades. So the educator's role is like shifting from just delivering content to now guiding learners, and through tools that are like constantly changing. We are seeing many plethora of tools that are coming up, and we are not able to catch up with every tool right now. And hands-on accessible platforms many companies, many organizations are providing, like IBM, Penny Lane, and much more. They are like giving us access to teach anywhere without any setup of very fancy elite lab, the need of that particular elite lab. And the real skill is the focus of not just learning a tool, but to uh, keep learning as technology shifts. So this is where I think that academia brings a very good depth and rigor, and the industry brings the relevance and the real problems. So the idea, this amalgamation, yeah, the students need both, because they also need to understand the academic rigor that makes, we can say, research oriented, and the industry oriented idea, which focuses on the real applicable problems. And we should move towards the research orientation should be move towards, and the industry orientation should also move towards the idea of user-centric, you can say, understanding, not just academia or industry-centric. It should be user-centric. So user at the helm, and how that can be done, we'll try to discuss that. So this is what I just wanted to connect with in very brief, that I'm very excited to discuss many ideas, many you can say things that need to be focused on. So yeah, thank you very much, Sheitul ma'am, and please continue, and we'll let us just start the session in some time formally.
Yes, sir. Thank you so much, sir. So now I would like to hand over the session to Mr. Amar Shivate to walk us through the LMS.
Very good afternoon to all the faculty members and the guest speakers. So, dear all, we'll have a quick LMS walkthrough. And in LMS walkthrough, we'll cover on the how you can join the daily session, about the attendance, about the certification, how we'll get the recordings or reading material, how we can mark our attendance on a daily basis. So all these things we'll cover into the next 5 to 7 minutes. So please listen carefully. So LMS is known as Learning Management System, and it's XLR online portal to get all e-learning content at one place. Okay. So almost of you are done with the registration. If anybody is still remaining, our team will be sharing the registration link over the Zoom and YouTube as well. So please make sure that you are completing your registration. Why? Because to get the LMS access, registration is important. And LMS is not just like we have 5 days of training program, and on this, for this 5 days only LMS will be available. It's not like that. In the future as well, after 1 month, 2 months, 3 months, it will be available where you can report the recordings and the reading material as well from the LMS portal. So once after the registration, you will find the 2 emails. You will receive 2 emails from our side. The first email with the subject LMS portal account details by XLR. Okay. And second email will be the welcome email, welcoming you for that particular FDP. So we're starting quantum computing today. So welcome to the FDP on quantum computing. Okay. So by using these details, we have to do a sign in. Okay. So here you can check the portal link, email address, password. By using these details, we need to do a sign in. And second email, this is welcome to the FDP on quantum computing by XLR. Suppose you receive only one email, that is a welcome email, and you not receive the login credentials email. So what is the reason behind that? So if you not receive this particular email, that means on LMS portal, your account is already created. Okay. And previously also you attended any FDP or SDP. That's why you have an LMS account. That's why we just added the new course, but same credentials you can use whatever you received into the past. If you are not able to remember, or if you are not able to search that email, then you can utilize the forward your password option as well. So I will show you that once we go on a sign-in page. So if I click on this link, mylearning.xla.com URL, it will take me through the login page. So let me just quickly reshare my screen and I will show you how login page looks like, where we have to provide the details and where we have option to forget our password. Yes, so once I click on the mylearning.xla.com login page, the page will look like this, and here I have to provide my details. Okay, so the first thing, if you are using the same account, you can continue with the Google as well. But we already provided the details, so sometime we'll use the different mail IDs. But make sure that whenever you are going to provide the details, whatever details you receive, provide that only. If you're not continuing with the same Google account, and as I said that there is one more option is forgot your password. In the scenario, you only receive an welcome email, you not receive the credentials, and if you're not remembering the password, whatever you received into the past, no need to worry. You can just click on forgot your password, add your email address here, click on the same instructions and just update password whatever you want and follow the same steps. Now I have my credentials with me. I have provided the credentials. I'm clicking on to the sign in. So what next? So once I click on sign in, so it will take me through the dashboard. Okay. And here you can check, you have many options on the dashboard, such as a back to home page, community, leaderboard, dashboard, purchase history. You have help button and you have profile as well. So we will go one by one. Okay, so first of all, coming to the profile. In a profile, you have an option that is the settings. Clicking on settings where you can manage or you can update your entire profile from name, email ID, mobile number, username, your photo. But the most important thing, if you want to update the password. So system generated password is a little bit lengthy, right? So in that scenario, you can update the password, whatever password you want. For that, you need to click on a profile, then settings, scroll down. In settings, you have option that update password. Okay. Here you have to type the password whatever you want. You can confirm that password once again, and once both the passwords are going to match, the update password button will be enabled, and from next time onwards you can utilize that password. Clear? Suppose if you're on a home page, okay, so here you are able to see the couple of courses as Akshay for short-term internship under AP government, or NASCOM courses, or SWAYAM plus courses. These are the credit-based courses. Suppose if you are here, make sure that clicking onto the profile, you are going on a dashboard, then only the things will be visible for you. So with the community and leaderboard, nothing to do with that. Community, it's called as sharing the information, but it's not open for you, as we're sharing all the information here and giving the LMS access. Leaderboard is something like a hacker rank or lead code. Those who are going to perform well, the students and faculty members. Like, I will open that. So there, all time who is leading the board, or we have around 8 lakh plus learners on the LMS portal, faculty members, students, right? So out of that, those who are performing well into the assessment, into the coding test, into the MCQ test, into the assignment submissions, or watching the videos, okay, or performing the assignment, so their XPS will be printed. Okay, so there we'll get the all time, this month, this week, today, all the leaders from the LMS portal. Now coming to the dashboard, where something which we have to go through in a detail. That first thing, that is a live session today. So dear faculty members, suppose today you receive a link to join the session on your email, but from tomorrow onwards you will be not receiving an email. You can directly use the links from the LMS portal and you can join the session. Okay, so for that you will find a live session today pop up on your dashboard. Click on that. Once you click on that, you will find the two links. The first link is a Zoom link and second link is a YouTube link. Okay, and by using these links you have to do a sign in tools to the LMS. So as my internet connection is a little bit slow, so it's taking some time. Yes, you can check here. FDP on quantum computing, June 29th, 2026, 3 p.m. You have a Zoom link and you have YouTube link. Clicking on this link, it will take you to that particular session streaming. Okay, if you're facing any difficulties over the Zoom, you can be a part of YouTube as well. Just whatever the things you have, or whatever the query or question you have, Zoom participant, you can just post into the chat box. It's open for you. You can chat with host and co-host. And for YouTube participant, they can put their queries into the live chat as well. So whatever the information we are also sharing, suppose now our team is shared the registration link, so that we share it into the chat box. So it is easy to share the details. So yes, clear on joining the session? Yeah. So next, how we can access the recordings, reading material or attendance. So once I scroll down here, below the live session today, I have an option that is enroll courses. So I have 147 enrolled courses. So on your dashboard as well, whatever the number of courses you are done, that will be available on your platform. Suppose this is your first FDP with Excel. Yes, so you will be able to see the one enrolled course, and that is the quantum computing. So first thing, that is the agenda. So in agenda, if you open that, you will find one ebook, and in that you will get the detailed information on that, what actually we are going to learn under the quantum computing for next 5 days. Below the agenda, we have attendance and feedback link. So dear participants, coming to the attendance and feedback link, this is a common link for attendance and feedback as well. First thing. Second thing, attendance link will be only open for 1 hour that for that particular day, and that will be accessible from 4:30 p.m. to 5:30 p.m. Today's link will be open at 4:30. It will be closed today only at 5:30. It will be not active after 5:30. It will be automatically closed. So make sure that you are submitting your attendance or you are sharing your feedback before 5:30. Now the link is already available over the LMS platform. So now a couple of you are just registered or not accessing the LMS portal as of now. So no need to worry, our team will be sharing the attendance link over the Zoom chat and over the YouTube as well into the live chat option sharp at 4:30 p.m. Okay, so you can utilize just clicking on that. It will take you through the Google form where you have to fill your details and you have to submit the feedback for the day from that particular link. So, dear faculty members, just one thing, please use a single mail ID while filling all days form, because every day the form will be different. Okay, and you have to make sure that 60 or more than 60% of attendance, then only you will be eligible for certificate. Okay, so this is a must. 60%, minimum 60% attendance is mandatory to get the certificate of participation. So we'll be sharing the link. If you are going to use the different mail ID, it will create your different accounts and you will not reach that criteria of 60%. So just make sure that for all 5 days, you are attending the session, you are marking your attendance and you are using the single Google form, and this FTP is open for faculty members. Okay, clear on marking the attendance? Yeah. So now I explain about the marking the attendance. So how about the certification? Yes. So those who are going to complete their course with 60 and more than 60% of the attendance, they will be receiving the course certification from the XLR team and collaborated colleges via your registered mail ID within 8 to 15 working days after closing the program. Okay. Yes. So we are clear on the attendance, feedback, how to mark, where you will get the link, and about the certification as well. What next? Live session, which I already explained about that. Yeah, Paramananda sir, yes, we'll be sharing the registration link again. No need to worry. Okay. So Sushmita or Sheetal, you can just share the link once again. Then coming to the session recording. So daily basis, day 1 to day 5, all the sessions recordings will be available here. You can check. If you click on a day 1, currently whatever the session is running, you will be able to see that as a session is running. But yes, once after completion of this class, today's class or tomorrow's class, immediately you will be able to see the session recording will be available here into the session recordings tab. Then materials, the important practice files or material, that will be also available over the LMS portal. Okay, so this is how you can access the LMS portal. And in the future, if you would like to connect with us, if you have any query, not now only while running the program, but in the future regarding to the MOU, regarding to the certificate or anything, here you have a help button. Okay, just scroll down. Here you have a help button. Type whatever the query, whatever the message, whatever the things which you have to share with us, and we'll get back to you as soon as possible via your email. So that's all from my side. Thank you so much for listening. And Sheetal, over to you.
Thank you, Amar. Now I would like to hand over the session to our subject matter expert for the day, Mr. Kishan sir. You can take over the session, sir.
First of all, I was just like to check, am I audible? Am I visible?
Yes,
Is
sir.
it, ma'am?
Yes, sir. You're audible and visible also.
Okay, thank you. Okay, so let me just share my screen. Is my screen sharing? Is this visible?
Yes, sir. It's being shared. It's visible.
Okay, thank you, ma'am. So let's start our discussion on the idea that is we are gathered for. So over the next, first of all, good afternoon, everyone, and welcome to this FDP on quantum computing. Over the next 5 days, we are going to demystify what is quantum computing together. And today is the foundation that everything else rests on. And a quick word that before we start formally the basic ideas, you do not need to have a physics background to follow this. If everyone can like just picture an arrow and read a bar chart, that will be more than enough, and we can move on with respect to that. So as we were just discussing earlier also, that this is the 5-day roadmap, and focus on the verbs that we are like seeing in here. That today we are focusing on the language, that the foundational idea, the language of quantum information. Tomorrow we will be focusing on the quantum states, quantum gates, and quantum circuits. That is specifically we will be building and running the circuits, and this will be done using the Qiskit pipeline, IBM Qiskit library or an SDK that specifically uses Python language. Day 3 will be about the famous speedups that come from the quantum algorithms that have been theoretically and conceptually demonstrated, as well as some algorithms have been in uh, good, you can say, showing good applications in different areas. Then the 4th day will be around how quantum computing meets machine learning, and we will look into the ideas of what exactly is a variational structure and some hybrid methods where quantum and classical computing are getting together to give rise to some new fundamentals, some new ideas. And lastly, the day 5 will be focused on the idea of the real devices, that how we can run our circuits on real hardware, not just on simulators, and what are the real applications. Very important point, that is NISQ, the current state of quantum computing we are living in, that is noisy intermediate scale quantum. And this was devised by John Preskill in 2018. While understanding that the current scenario is that we are living in with respect to quantum computing is we have to handle noisy data, and how this can be mitigated. And lastly, how this can be integrated into classrooms. So the understanding is that each day stands on the one before, and so the ideas that we will be discussing today, they matter the most. And as iterated again, earlier, that we will not be assuming too much of quantum mechanics, and also the mathematics will be, you can say, we will use it as judiciously as we can use. It will be very less, no, you can say, deep discussion will be there. We will be just focusing on what exactly is needed. Now, coming to today's agenda, it is divided into 4 parts. The first part is the introduction and motivation, where we start with the idea that why this field actually exists. Second is the idea of the small amount of mathematical language we need, specifically the bracket algebra that comes from the idea of Dirac notation, and the idea of Hilbert spaces. Very fundamental idea. The If some of the faculties are from mathematics background, they must be knowing the idea of vector spaces, specifically the deep dive of vector spaces, and the idea of abstract algebra, that how it is pivotal in the idea of this. It is the backbone for this Hilbert space. Then we move on to the 5 fundamental ideas that make a qubit, that is the quantum bit, different from a classical bit. Yeah, specifically the ideas of superposition, measurement, then interference, entanglement, and the qubit itself. And lastly, what's the ecosystem currently, how do we run our circuit. We'll do some hands-on based on this, that how to run a quantum code, what's the setup needed, and what's it. We'll specifically see the difference between a simulator, when we run on a simulator, and how we can run it on a real hardware. There are many setups, many we can say organizations that are running the coming up with new tools, but we will be specifically focusing on the IBM Quantum's Qiskit platform, and we'll run our first circuit. So in any case, if anyone feels that they are not understanding the whole paradigm, they can come back to this particular map, that how it actually is stacked up. Now, the problem starts with the understanding that this is a kind of a simple puzzle, that a caffeine molecule, or a caffeine, you can say a particular molecule, has just 24 atoms. And we are not going into the chemical aspect and now. The understanding is that we just need to understand that, okay, caffeine has just 24 atoms, the structure of it, and yet representing, or you can say simulating it, is not possible, even from with the idea of the powerful supercomputer we have on the earth. It is not able to simulate this particular caffeine atom. And this is an estimate from IBM, that we need to have the an order of 10 power 48, you can say classical bits. But for instance, you can understand that the Earth is itself roughly 10 to the power 50 atoms. So what about if we have some problems that are more, you can say, complex than this caffeine atom? So the problem that we are seeing is that the machine is not slow. It is doing a billion operations a second. The problem is that the difficulty is coming from that describing the molecule's quantum state. It needs more numbers than there are atoms on the planet. And this is what the gap is all about. And hold on to this gap, because this is the exact reason why this field, that is quantum computing, exists. So the idea is that every era of computing has cracked some problems, and the previous one, that the previous era that couldn't solve some problem, the next era has era of computing has solved comfortably. And if we see in retrospect, each new era has been a complement, not just a replacement. So quantum is the next link in that particular chain. So do not leave today's you can say session when you leave today's session, you do not think that quantum computers will going to replace your laptop right away. They won't. They are just a specialized tool for a specific class of problems, and we will be focusing on that which problem is like dealt with which particular you can say uh, algorithms or any other computing paradigm. So the idea that we are understanding that the focus is on complexity, not just speed. So when we describe this n two-level quantum system, we are requiring this 2 raised to power n complex numbers. So it means each particle is focusing on what it is just getting doubled. So even this 50 systems, that is 50 you can say particles, they need petabytes of memory and so on. If we go on towards 280 systems, it is like what, 10 raised to power 80. This is the exact atoms in the observable, or you can say approximate atoms in the observable universe. So the problem is that each quantum particle we add is like doubling the information that is needed to describe these particular systems. And this is an exponential growth, and no amount of faster hardware that we have that in classical computing, it can catch this particular idea. So hardware is creeping up linearly while the problem is exploding exponentially. So we are coming to a conclusion, a very important conclusion, that the answer can't be a faster classical computer. It isn't. It has to be a different kind of computer. And this is where the great Richard Feynman, his ideas come up that this is a kind of a leap. These particular words that nature isn't classical, and if we want to make a simulation of nature, we have to go towards some quantum mechanical phenomena. So quantum mechanics has been in prevalence from 1925, but the idea of quantum computing, it gained, you can say, a good amount of speed up after this idea that Feynman discussed, and there were discussions all around. Paul Benioff is one of the other pioneers that who was focusing on quantum information theory and many things like that. But this idea, that focusing on quantum mechanical properties rather than just uh, understanding the nature classically. So this is the founding idea of this quantum computing, and we have seen some proven you can say advantages in the form of Shor's algorithm and Grover's algorithm. So Shor's algorithm has shown an exponential speed up for integer factoring. So it seems very simple that okay, 15 when we try to factor 15, it is okay that 3 into 5 we can do that. But what about if I give a 10-digit random number? How much time will it take to factor that particular integer? So it becomes problematic for the, you can say, fastest supercomputer that we have currently. So this is where the idea of Peter Shor's algorithm comes in. And as for Grover's algorithm, he's specifically from India itself, and his algorithm focused on the idea of unstructured search, and it is giving us a quadratic speed up, and that is in itself is very advantageous. So these are real proven advantages, not just hype that okay, we are getting some imaginary advantage. It is not like that. As well as we do have some simulation of chemistry and materials, and we are moving towards the idea of drug discovery and other associated areas there where this particular advantage is coming up. Now, we also must understand that where there is no advantage. So in everyday tasks that we see, that email or spreadsheet, graphics, classical is definitely winning there. No doubts about that. And a few areas like optimization and machine learning are promising, but is still unproven. So when we say that okay, we will venture into the idea of quantum machine learning, uh, we will focus on what exactly is advantages there and what are the problems, whether it is a hardware problem or a software problem. And this is the whole stack that we will be focusing towards. So one specific learning, you can say lovely thing about this field is that it is genuinely interdisciplinary. So whatever you can say departments everyone is coming in, there is a way in every time, whether it is physics background, mathematics, computer science, electronics, chemistry, AI, or anything else. So the focus now is that there is more than one way to build a quantum computer. And currently, the model that we are harnessing, that we are using, uh, focusing on so much is the circuit, or the we can say circuit model or the gate-based model. This is a complementary model of the von Neumann architecture or the Turing computing that we see in classical computing. And the focus in here is around the unitary gates that we will be seeing in subsequent sessions, that single qubit gates and multiple qubit gates. And we will be focusing on this particular modeling, that how Qiskit uses it. Then another idea is the measurement based model that focuses on some clustering estates and how to do some single qubit measurements. Another model that comes up is very famous model, and adiabatic computing is one part of that. We focus on the ground states of a Hamiltonian, and another is the quantum annealing. And this quantum annealing is the you can say basis of the D-wave annealers that have been in quite prevalence for the last 15 years. I think 12 to 15 years, because they have been like coming up with that. So D-Wave is a pioneer in the idea of handling the ground states. The system is how the system is evolving, and it is staying in the ground state. Then one more specific model that is still in its experimental phase, and it's very important to understand the idea of topological quantum computing, where the information is stored in the forms of an anyons, and the entanglement is somewhat now built up using the vertex and placket operators. So this is the basic idea around topological quantum computing. And lastly, regenerative is not as per se currently a model. This is what I am exploring and researching on, which is so just a small introduction to that. That it is focused on that. What I am exploring is how dynamic reconfiguration is like driven by the semantic rules and goals. And actually, this is complementing the kind of a coherence optimization. So uh, these models are like all equivalent in power, and each can simulate the others. So they actually differ in hardware and engineering trade-offs, and not in what's actually computable. So the circuit model that we are focusing on is, as iterated, that it is like the quantum concern of the classical logic circuits that the computer scientists already know. Okay, so a quick bridge between what is the classical part and what is the quantum counterpart of that. This is the, you can say, a kind of a single most useful slide to anchor the whole understanding of what exactly is needed, and you can keep coming back to this. So every idea that we are seeing that a bit in classical is a deterministic idea, whereas a qubit, when we move on to the idea of qubit, that is a quantum bit, is what it is in a superposition. And now what exactly is a superposition, we'll discuss that. No need to worry about that. But it is in a superposition until measured. It means there is no definite answer right now, that until it is measured. When we measure it, when we measure the qubit, then we are getting a deterministic answer. So we are getting a deterministic answer, but only after measuring. In the terms of classical idea, we have the logic gates, somewhat like and or not, and likewise in quantum computing we have unitary gates where we focus on the x. This x gate is same like the not gate that we have in classical computing, but besides that, every gate in you can say quantum paradigm is a little bit new and different from what we have in logic gates in classical paradigm. So Hadamard gate, C0 gate, many others are there. Now comes up a very important aspect, that the classical operations are irreversible. That is, gates erase the information. When we apply AND gate or any OR gate, we are not able to know that what exactly was the starting point. Whereas in the quantum, the gates have an inverse. Every gate has an inverse, but the you can say the operations in the quantum computing, one sole exception is there, that measurement is not reversible. As soon as we measure the premise, the answer that we are getting is now turned into classical answer, that is a deterministic answer, so we can't retrieve that back. So this is a deterministic understanding, that we have one fixed output, whereas in the quantum computing we have a probabilistic output where the outcomes they are actually focused on the idea of amplitudes, how amplitudes are made up. And we have the understanding that when we have n bits, we need to have 2 raised power n possible states, and these have to be processed one at a time. Whereas in the understanding of quantum computing, 2n qubits are powering the idea of these Hilbert space, 2 raised power n dimensional Hilbert space, and these are all amplitudes at once. And this is the most powerful idea in the understanding of this, you can say, the connection between the classical and the quantum computing. As discussed earlier, that von Neumann model and the circuit model, these are like somewhat the quantum analog. And another great idea, a very, very great idea that we will be discussing throughout today and tomorrow specifically, that is, there is no copying restriction. It means we can copy a state from one place to the another, just like we put up the gates and all. But in here, the idea of quantum computing is based on this, that we can't do any cloning. There is no cloning algorithm, that is theorem that is there, and we can't copy a particular state. So the idea is that each of these will unpack them over the next you can say the whole hour, and understand that what exactly is happening in every aspect, from every aspect. Now we'll focus on very little maths. There is very specific ideas that we will focus on: vectors, matrices, and the bracket notation. This is the new idea that I hope everyone is somewhat versed with the basic idea of what is vector and matrix, even then we will be focusing on that, and the bracket notation that is coming from the Dirac notation. So the idea is that think of this as the learning as the the alphabet of a new language, just like we learn some new language. And the idea is that the focus needs to be you can say understood, that we how the bracket notation is helping the cause of a qubit and associated ideas. So the quantum state, as we see, is a vector, and a quantum gate, as we understand, is a matrix. And we'll see this specifically, that how this quantum state is being shown, and whatever the outcome probabilities we are getting, they are coming from the amplitudes. So the focus in this understanding, that is the amplitudes, is what a quantum amplitude isn't just a basic size, it is also carrying a direction. That is, we have some direction, as well as and that this particular direction is actually called the phase. So magnitude plus phase, they make up an amplitude. Right now it might feel useless, like, okay, why are we discussing magnitude and phase and all? But this is important in the context that the idea that phase is the secret behind everything quantum can do that classical can't. Phase is the most important idea, and this phase itself, as we understand, that if we have two amplitudes that are as at opposite, you can say pointing opposite, then that is the way of saying that we have a destructive interference or the destructive idea. And if they are at the same pointing towards same you can say side, it is a kind of a constructive idea. So the idea of this phase, how it is pivotal, will we are trying to unroll that. Now the question is that how do we write this qubit with the help of this amplitude and all that, the magnitude and the phase, the two things that we have as we are starting, that a quantum state is written in the form of a vector, and this contains two specific idea, the magnitude and the phase, and how this can be used to write a qubit. Now qubit is what? It is a column of numbers, as we are specifically understanding it, and it is a vector. How? That 0 and 1, as we say, using a ket notation, that is this is a ket notation from the bracket idea. It is just simply used for the labeling and to say that this is a quantum state. And these brackets are this bracket in itself is the new language that we are just that we were just discussing. So this 0 and 1 will actually be seen as the north and the south poles of a sphere that we will be meeting shortly. And it is somewhat same ideas that we will seeing in two different from two different aspects. And this 0 and 1 is the computational basis state that is needed. So this 1 comma 0 or 0 comma 1 is actually telling us that which part of this idea is present and not present. Now, let us formulate this idea through the, you can say, one of the most fundamental pivotal idea, and that is the idea of superposition. I hope everyone will understand this superposition quite easily, because this is the, you can say, kind of a headline idea that it might sound mystical, but mathematically it is just adding the two basis states with weights. nothing else. It is just we are adding two basis states, that is 0 and 1, with some weights. And what are these weights? These are amplitudes. And as we discussed amplitude, what is an amplitude? It is an combination of a magnitude and the phase. And so the magnitude part is giving us the weight part, and the phase is giving us the direction. So the weighted combination, as we see, the weirdness that we might expect, that okay, how this seems a little bit weird. It is not coming from this particular equation. It is from the idea that what happens when we measure this. It is not coming from this particular idea that okay, this equation is somewhat messy or a kind of a weird. No, nothing like that. Right now, it is the idea, an analogy of this particular idea is that the Schrodinger's experiment, the cat experiment, that whether the cat is dead or alive, it is a very profound experiment. And it is like one of the, we can say, guiding idea that how we can understand superposition. So right now I'm standing like here, like, or maybe sitting in here, and I just want to know whether the cat is actually alive or dead inside this box. I can't with 100% surety, that is certainty, can't tell that whether this what's the position, what's the actual you can say scenario, until and unless I open the box. I will not I would not able I wouldn't be able to like decipher that what exactly the state is like. This is what the idea of superposition you can understand, that okay, whether it is 0 or whether it is 1, we are not saying that it is a kind of a superposition. It is a 0 and 1 at the same time, simultaneously. This is the most important idea, because as soon as you understand superposition, another the next set of ideas, whether it is interference, measurement, entanglement, and many other ideas, they come along. So that is why we're saying that the weirdness is focused on with the idea that how when we measure, then what actually happens. So we'll come to that just in 2 or 3 minutes, that what exactly is happening when we are measuring. Right now we are not focused on the measurement. We are just focused on that okay, there is some condition that okay, that whether the cat is dead or alive, we are not knowing. We'll try to unbox it, or try to take out the box and see that whether what is the exact condition. So for now, the idea is that the qubit is a weighted mix of this 0 and 1, you can say, state, this basis state. And alpha and beta are the complex amplitudes. And this is with regards to one qubit only. That is, we have one qubits, and through that one qubit, we are able to show two different basis states. And this is the idea that we just discussed, that one qubit, it will from that we can have 2 raised power n dimensional Hilbert space. That is the basic idea with classic computing also. But how that is processed, this is processed sequentially. Even after parallel computing, you can't able to you won't be able to do that much you can say at that particular scale. But all amplitudes, when we say that all amplitudes are seen at once, what exactly this means, how quantum computing is different from the classical parallel computing. Because it is a misconception that okay, we are understand the idea of quantum computing is just the idea is just the idea of a new kind of a computer that is doing everything parallelly. It is not like that. It is nothing like that. Okay, so this amplitude, as we have been discussing, is very important. the weights that we are discussing aren't probabilities directly. They aren't probabilities. We have to square them to get our probabilities. That is, we need to do some normalization and then square them. And this is what the bond rule is all about. So, and this is worth remembering because the idea is that amplitudes, that is the alpha and beta, as we see, they can be negative, but the probabilities never are, as we understand from the basic idea of probability. So this negative sign is exactly what lets to amplitude cancel, as well as this and this cancellation is actually where the quantum advantage will come from. So now I hope everyone is understanding where we are going towards. The actual advantage is not just coming from the idea of superposition. It is not just that okay, we can see multiple states at once. Nothing like that. It is just one, you can say, a key part in the understanding of where the advantage is coming from. So the idea is that this the cancellation of amplitudes, or the you can say addition of amplitudes, this is the very profound, very key part, very important part in this understanding. So as we say that this sign or phase is precisely what allows the amplitudes to cancel. So the idea that we discussed, that okay, we are seeing that a quantum state is a vector. We have discussed that in quite detail, and a quantum how a quantum gate is a matrix. We are just moving on to that particular part, that if states are vectors, then operations that are being applied on them are like what? That are gates, are matrices. And the important property that makes this possible is unitary. That is unitary operation or the unitary evolution, which just means that we can do some reversible operation, and every quantum gate can be undone. That is, if we apply some quantum gate and we again apply it, that it will come back to its original state. So just like trying to picture it as a rotation of that state arrow. This is what the basic idea is, that we are just doing some rotation of that particular state. And one of the like the exception that we earlier seen very briefly, that measurement is not a gate, and that is why it is irreversible. It is an exception that comes up. So will understand that why exactly this exception is coming up. This is very, very important. Now, there's also one key point coming up in here. Right till this point, we have like seen many new terminologies, and it might be it might somewhat get confusing, that okay, what exactly is this new terminology actually telling us. So try to just see through for some more time, and we'll understand it, what exactly you will understand the whole in context, that what exactly is building up. Also, the idea of this single qubit gate, as we have been discussing, we haven't discussed till this point anything more than that. We have just focused on a single qubit right now. So this single qubit gate is like a rotation on the Bloch sphere, and this Bloch sphere is just a representational view. When we will be doing some hands-on, we will be discussing this. We'll seeing this Bloch sphere in detail. Next, we have seen how state is a vector, how gates are being used. Third idea that we have in mathematical understanding is this bracket notation. Very, very simple idea, and this is purely for convenience. The gate is our column vector, and the bra is the mirror image of it, that is the conjugate transpose of it. And as we put them together, we will be getting a single number, whether it is giving us a kind of an overlap, that is some identical states, or whether it is you can say orthogonal, that is they are perfectly distinguishable, or anything like anything in this state. So the only idea that we need to carry forward in here is that overlap of one means the states are identical. So when we are seeing this, that is, this is the phi state and this is the psi state. That is when we are taking the inner product. We can do the outer product also. When how this is stacked, if you see, this is bra and this is ket. When we are seeing the bra ket, when we see it in the terms of ket bra, oh sorry, bra, yeah, sorry, yeah, ket bra. It is when we put this first and then this, then we will be getting an outer product. So what exactly is inner product? Inner product in here, it is just a dot product. So we will be getting the basic idea, fundamental. If you see this from this idea that 0 and 1, what is 0 in here? This 0 state. This 0 state. And what is the 1? That is this 1 state. And when we do the basic dot product of these this 0 and 1, we will be getting 0 itself. Let us try to see that. Let me show in here. Yeah. If we are multiplying, making dot product of this, 1 into 0 plus 0 into 1, that is as simple as it can get. This is the inner product or the dot product that we will be getting. But if we have something like 0 and 0, that is both of the states, that is the idea around this overlap. In that we will be getting what? 1 comma 0, and another state will be like 1 comma 0. So we will be getting 1 into 1 plus 0 into 0. So this gives us a single you can say answer, a number, a particular number, that is 1. So this is where the idea of overlap, that is the identical states, and the perfectly distinguishable states comes up. Now everything we have discussed in this mathematical understanding or is coming from the idea of this Hilbert space only. This is where the quantum states are actually exhibiting their idea. So it is just the formal name for the arena we have just discussed till this point, that we have vectors with an inner product, and for qubits it is finite and it is friendly, but as we are understanding that one qubit, it lives in a two-dimensional space. So if pertaining to one qubit, we are saying that this is the basis states that we can see. If we move to move towards multiple qubits, 2 qubits, 4 qubits, and anything like that, this basis state will be changing along that. So as we just saw the inner product, that is the idea of how n qubits give a space of dimension 2 raised to power n. That is where the exponential advantage and gain is coming from, and this is the resource quantum computers exploit actually. So everything we have discussed till this point, that is states as unit vectors, gates as rotations, and the inner product is giving some overlap, all of it is just living in this particular space, that is this Hilbert space. So the term isn't this idea of Hilbert space, isn't a new kind of machinery, it is just a name from what we have already discussed. So a quick checkpoint of what has been discussed. The idea of amplitudes, that how the size, or you can say the magnitude and phase is you can say being amalgamated to give a possibility, and how the vectors are, the quantum states are seen in the terms of vectors. What exactly is a quantum gate doing as specifically some reversible rotations, how the bracket notation can be used to give some you can say compact notation for states and overlaps, and the idea of the Born rule, specifically that we need to focus on the amplitudes square, not just the probabilities. So is there any questions till this point? Let us move towards the 5 core ideas. Let me check the chat. That's there is a question that the ket representation is a column vector, but in previous slide it looks like which slide? Can you like point it out? Dhanlakshmi ma'am, can you point it out? I hope it is okay. Yeah, it's okay. It's no problem. Yeah. Okay. So let us move on. We'll come back to if needed. So the 5 core ideas that we have from the understanding that we have seen till this point, these 5 ideas actually separate a qubit, that is a quantum bit, from a bit, and they build on each other in order. That is, a qubit can be in a superposition. This superposition is collapsed, or we collapse this superposition using the measurement. The measurements, when we measure it, the interference steers the state, whether it is constructive interference or destructive interference. There are 2 different types of interference, and the entanglement links them. Very important note: superposition, when we discuss, it is with respect to a single qubit. That is a single qubit. Whenever we are discussing about entanglement, it is 2 or more qubits. So each is building on the previous one, and as we understand the basic ideation, the next days, that is 2 to 5 that we are subsequent days, we will be applying these 5 specific operations, and how this can be this will be done. This is what we need to focus on. So a quick note on what a bit and a qubit is. I hope everyone is now understanding. A bit is like what a classical light switch. That is, we have just on and off, and at a time we can have one state only. It is a deterministic idea. Whereas a qubit is like a kind of a dial or a dimmer. That is, it can sit anywhere in between. It is kind of a continuum, as we are understanding. Until unless, every time if you see the idea, the qubit, we have specifically seen this, that it is the idea that until measured, until and unless it is measured, it is a kind of a continuum or a kind of a dimmer switch. So here is the catch that needs your attention. The moment we read it, that is, or we measure it, the dimmer is that the idea is snapping to either fully on or fully off. That is, it will be behaving like 0 and 1 only, nothing else. It will be like then focus, either coming out to be deterministic 0 or deterministic 1. And this is where the infinite possibilities are residing inside it, but only 2 possible answers we will be getting from that. Only one of the 2 outcomes we will be getting, whether it is a 0 or 1 as iterated. So this is the basic fundamental between this bit and qubit. Now the idea, as we were discussing, the Bloch sphere, very important idea. Why? Because how are we going to show, are we going to build up on the understanding this particular state where it lives actually. So every possible state of the qubit, whether it is 0 or 1 or anything like that, 0 and 1, it is a point on this particular Bloch sphere. And top, that is the north pole, is definitely 0, and the bottom is definitely 1, that is the south pole. And everywhere else is a superposition. Everywhere else is like what? A superposition. We do not need the coordinates. We just read the positions, that what position is a particular qubit is in. And high means it is very likely 0, and low means it is very likely 1. So this sphere is like kind of a map, and not just a tiny physical ball. Okay, so the idea, I think there is one question. What's that? Question is, can we say that it is similar to binary language concept? Yeah, ma'am. Yeah, it is similar to binary language concept. We are seeing that it is same understanding, that is the binary concept only. We haven't discussed anything other than that, other than 0 or 1. But what exactly we are saying, that this idea of 50-50 involvement, that is something is 0 and something is 1 at the same time, that is simultaneously. This is where it is important. And when we discuss about classical computing, we need to have some definite you can say answer as soon as we apply some operation in here. Even after applying numbers of operations, maybe hundreds of operations on some qubits through gate operations, if I am not measuring it, if you are not measuring it, we will not be getting a definite answer. That's for sure. It will still be in a superposition, and it will be a 50-50 superposition, equal superposition. As soon as you go away from it, that is whether if you go away from these points, this other points, you will be getting some specific answer, whether it is 0 or whether it is 1. This is what the basic idea is all about. Now, as we understand, so if we put a qubit on the equator, it will be an honest 50-50. And stress, we must put stress on the word honest, because it is not that the qubit is secretly one value and we are like ignorant to the other one. It is genuinely balanced between the two, and the position on the sphere is telling us the exact odds. So as we tilt it towards a pole, we will be tilting the odds. So this is what the basic idea is all about. That on the sphere, it is kind of a mix of 0 and 1, but when we put it to a closer to a pole, that outcome is much more probable. If there were no superposition, would a quantum computer behave just like a classical computer? Yeah. If there is no superposition, then the idea is actually just classical idea only, because superposition is giving us the understanding that, okay, how we can get simultaneously two different states at a time. Whereas in if we do not have any superposition, any idea like that, it will actually be same like this, the understanding of what we see in the terms of classical computing. So it's the understanding, that is how particular you can say concept, this particular concept, that superposition is kind of a starting point, the first point towards understanding that how what type of quantum advantage we are like moving towards. Okay, another question is that I understand that quantum computers can solve certain problems much faster than classical computer. If that's the case, why don't we replace classical computers entirely with quantum computers? What are the limitations that make both classical and quantum? Yeah, ma'am, that's a very good question, and I would uh, yeah, I would like to answer this a little bit later, because it is very important in the sense that, okay, we we can be inclined towards I'll try to take it brief, and we can discuss this a bit more towards we can say end. So the idea is that if we directly just replace quantum computers, classical computers with quantum computers, then what exactly the specific problems are we able to solve today? This is what the understanding is. There are many problems that we are striving towards, that can be solved through quantum computers, but not entirely. Not every problem is being handled can be handled through quantum computers. So the focus that we are currently seeing, and it will be a kind of a trend in you can say kind of a you can say trend for next 5 to 10 years, is a kind is the idea of hybrid computing that we will be discussing in the later parts of the day, that is the third and the fourth day, and we will be specifically focusing on that, reinforcing the idea of how classical and quantum computing can be join together to come together to have a more enriching experience. So I will try to keep it right now as brief as possible, and we can discuss this at the end of the day also. Okay, so the idea of qubit, as we were discussing, so outcome is like what it is. If it is closer to a pole, it will be more probable, as we just see at the north pole or the south pole. Then what superposition and is not actually. A superposition is not a hidden idea, that is just we were discussing it. It's already 0 or 1. It is not like that. We just don't know. The problem is that we just don't. It is kind of a black box. Go back to the idea of Schrodinger's cat experiment. Until and unless we are opening the box, we actually don't know. It is kind of a black box. We do not understand what exactly is happening inside it, whether the cat is alive or cat is dead. So a spinning coin is already heads or tails under your hand. A spinning coin, as we say, it is a classical coin. We say that, okay, whenever you spin it, it is definitely coming as either heads or a tails. But a qubit is genuinely not decided until and unless, again, that same point measured. And one more myth that is there: a superposition does not store 2 bits. It is not storing 2 bits. As soon as we measure it, you will be only getting 1. It means the idea that is coming is that the understanding that we are at some stage where there is some simultaneous computation happening. So this is what the basic idea. Okay, there is another question. What's that? The question is each measure will give a different value. That depends. That how many times we are measuring it, that we will be covering in a few minutes. That if we are giving it 10 shots, that is 10 trials or 100 trials or 1000 trials, based on that we will get different you can say probabilities. So moving on, the idea, the holy grail, that measurement, as we have been reiterating again and again. What exactly is measurement? It forces that it's smooth superposition that we have. It snaps to either 0 or 1, and then super is gone for good. That is, we are not in the superposition. That is, the states it is not in superposition. So two things make this profoundly non-classical. Why this idea is non-classical? Because it is irreversible. First of all, we can't reverse it. Why? Because when we are opening, now let us rhetorically open that box of Schrodinger's cat. As soon as we open the box and we see, okay, the cat is alive. Now we can't go back to the state that, okay, when we were saying whether the cat is alive or dead. So we have now observed, we have just seen that, okay, the cat is alive. So this can't be reversed. And the act of looking that we are doing in the process, it changes what you are looking at. So what exactly we are saying? That you can't peek at a qubit without disturbing it. And a quick idea, that this is where the fundamental understanding of quantum communication, it kicks in. That currently, if me and my friend, or me and my mother or father are in a call, it is a possibility that anyone can intrude in, and we won't be like alerted. We won't know. It is a possibility. Maybe they are using very high some good RSA encryption technique, decryption technique, and they are like intruding into my chat. Just like we see in WhatsApp, it is written as that this is chat is end-to-end encrypted. How it is an end-to-end encrypted? That one party can see the other party, and second party is seeing the first party. The company can't check it. The company can't like see it, what exactly is happening. So in quantum computing, what's the understanding is that as soon as if Alice and Bob are communicating, they are in you can say constant communication, and as soon as Eve, that is the eavesdropper, it tries to intrude, this communication will break. This is what the measurement is all about. That Alice and Bob, they are the two specific persons. This is the basic understanding of communication. There is a communication going on, but as soon as we intrude in any sense, even a small noise, even a small change will break that superposition state. And this is what makes measurement so profound and very and different from the idea of how and it makes it non-classical. So that is why we say that we can't read out all the amplitudes. We will either if we get 0, we will be getting either alpha, or if we are getting 1, we will be getting beta. So I hope everyone remembers this. A quick check on this. If we are getting 0 as an answer, we will be getting alpha as amplitude. If we are getting 1, we will be getting beta as amplitude. Okay, now moving on. Now this is I'll try to make this as brief as possible, and we will be discussing this in the next session, that is the second session, because this is a somewhat more abstract idea, and it becomes quite heavy on the understanding of what exactly is there. There is the idea of the phase that we were discussing, the global phase and relative phase. So global phase is unobservable. That is, it is an overall spin of the whole state, and it is completely invisible. We can't, nothing can detect it. Whereas the relative phase is the difference between this 0 and 1. That is, we are seeing in the sense that plus a state, just take it as some state. There is some state. I'm not saying that we are not. I'm not expecting currently that what you need. You know that this is some state. Just take it as it is. We'll understand what exactly is this. This plus state is giving us the superposition. This superposition 0 plus 1 root 2, and this minus state is giving another kind of superposition. What is separating both of these states is this plus and minus sign, nothing else. This is what the basic idea is all about, and this is why these two states are different states, and how these states are built up, how these states are produced, will come to that as we move towards the idea of the quantum gates. So everything will be covered in that particular idea. For now, just observe this. This is some profound idea coming up. Another idea that we this particular understanding that how measurement basis and is used, we will be coming back to these ideas in day 3 and day 5, where we choose the direction we can measure in. So plus and minus, they look identical. They are both 50-50 if we measure the usual way. If you see this, if we take it as in the terms of the state, this is 0 state, this is 1 state, this is 0 state, this is 1 state. It is same like this, but just the difference is in the terms of this sign, nothing else. Other than that, magnitude is same, phase is different, the phase is changing only. So but when we measure in the right direction, they will be perfectly distinguishable. So the idea that is coming from in here is that phase is invisible until we look at it from a correct angle. So this idea is actually the seed of quantum cryptography, and that is what you can say stems the idea of quantum key distribution of the PV84 protocol, that is very pivotal for breaking the RSA encryption and the idea of saying of very famous understanding, harvest now, decrypt later. That is, anyone can, if they have a very good, you can say, decryption mechanism and anything like that, any intruder can like procure the data today and they can harvest it later at any point of time. This becomes very problematic because now our data is not safe in that sense. So yeah, we'll come to that understanding what exactly happening in that in this state. Now, quick question that was asked: one shot or many shots? It gives us the understanding that one run gives an outcome, and that tells it just gives us an outcome. It doesn't tell anything about that. When we run it multiple times, this is where we say about it that we need to give it different many shots, and from here we understand that how a quantum result can be read, and what it means to read a bar chart, and it will never be a single number. A very quick note: I am seeing there are many questions coming up. As I have to like accommodate some hands-on also, I'll try to answer these questions at the end of the session. So please bear with that because we need to see some basic understanding of what exactly is happening in hands-on part. So yeah, you can send your questions in. I'll happily answer that at the end of the session. So the idea interference, this is the real advantage. Now this is the most important idea in the entire context, that randomness alone isn't powerful. That randomness coming from what? The idea of interference. A coin is random and useless. It can be that. The magic is interference because amplitudes have phase, and we can make wrong answers cancel out and right answers reinforce. This is what the constructive and destructive phase is all about, and this is this particular idea is the backbone of the Grover's algorithm, which is Love Grover's algorithm. A very profound idea. Every quantum algorithm you will ever hear about is at its core a cleverly engineered interference pattern. And I just gave you a quick example, that is the Grover's algorithm, where we focus on those you can say answers only that are those patterns only that are to our liking, and just cancel out the other patterns. And this is where when I say when I said that okay, parallel quantum computing is not just the idea of a parallel computing, that is we are checking every possible solution. No, we are not checking every possible solutions. We are doing what? We are specifically doing this idea, this is interference, canceling out you can say useless outcomes and reinforcing particular specific good outcomes. This is what the idea. How it is how this is done, this is the matter of another context, that is the oracle function, the black box function. We'll discuss that. So interference, as we understand that it is kind of a physics that is applied in noise cancelling headphones that generate an opposite sound wave so that the noise vanishes. So quantum computer is like just exactly doing this, but with computational possibilities that that instead of sound waves. So why it works? Because if there is no interference, there is no quantum speed up. So both ideas are needed, superposition as well as interference also. Superposition will be focusing on exploring many possibilities, whereas interference will be focusing on what? Concentrating on correct probabilities before you can say measure the answer. So even if we drop either of the half, we will be getting nothing. So a superposition is just focusing on what? The a single measuring hands, you can say a single random guess, and we need to have a combination of both. So this honest framing, we need to frame it honestly in this sense that this is the best defense against quantum hype, that this we are doing this, we are doing that. It is not like this. We are focusing on these two on these particular phenomena. Then comes up the idea of entanglement, another idea. Now this idea is like the most overhyped idea that you can see. Many different idea, you can say, understandings have been discussed, but the idea is that the two qubits, they can be linked so tightly that they share one joint state. Let me repeat. We are saying that two qubits, they can be linked so tightly that they share just one joint state. And as soon as we measure one, you will instantly know about the other. But it needs to be understood that this is not just this is not any type of fiction. It is not faster than light messaging. The outcomes that we get are random and we can't control them. So no information is actually sent. It is actually what it is, not communication. It is, as per se, it is correlation. So classical correlation techniques, as we see different correlation technique, whether it is a Pearson correlation or any other you can say correlation technique in statistical methods. Just like that, we have some another idea in quantum computing, that is exhibiting the idea of correlation. There is no classical counterpart of this in you can say in classical computing, but the idea is that we are seeing some correlation between two qubits, and if the states are separable, then they are not entangled. If the states are inseparable, then we say that they are entangled. So if we understand this from the context point of view, that how this can be made up, it is done so using a bell pair, and the idea that how the outcomes come up, that is 0 0 or 1 1, that will uh, exactly built in the day two, that we will be focusing on, and briefly seeing that today itself, that no pair of independent classical coins can do this particular understand, that each qubit is exhibiting the idea of 50-50, but as soon as they are perfectly correlated, we can't point out that whether that any you can say classical coins can exhibit any idea like that. So that's the basic fingerprint of entanglement, and we will see that how this actually is you can say built. Now, a very quick checkpoint, and then we'll move to the you can say hands-on part. We are running out of time for today. So the quick checkpoint idea is that we understood the qubit, superposition, measurement, interference, entanglement, and these five ideas are the basic you can say ground for the circuits that we build, the algorithms which that we build, any idea pertaining to quantum machine learning, quantum AI, or anything like that. This is the basic idea. Optimization, security, healthcare, finance, logistics, anything like this, any you can say application, it will be built using these particular ideas only, nothing else. Okay, so now I'm not going into the theoretical aspect of where this quantum code runs and all. This can be this is perfectly okay, and this everyone can understand this, that how the we run on the simulator or quantum computer. I am going to focus on the first quantum circuit that we can understand. Now, currently, this looks like something new. Even everyone is like a capable faculty in here, but yeah, this is a kind of a new idea that we are seeing in here. For a quick understanding, first of all, I will be sharing one installation guide of Qiskit that is hosted on YouTube by IBM Qiskit itself, and let me show you that quickly. So this is the guide to how to install Qiskit and how we can do coding with Qiskit. that is the 1.x, and now we have moved towards newer versions and at 2.x. It is a very simple, straightforward video. I will be pinning it, sending it to the team, and they will, from there you can come up with the installation process. Specifically, this needs Visual Studio Code, the Anaconda platform. You will need to build a virtual, you can say, environment in Visual Studio Code, and then there are just 2-3 specific libraries that needs to be installed, and then you will be good to go. So moving towards the idea that how actually this runs. If I hope this is okay with everyone, it is okay, visible to everyone. Right now, you do not need to fret about that. What exactly is this? How it is coming up? This is just the whole setup that is perfect and done perfectly. So we specifically import some libraries. NumPy, SymPy for some calculations. The important library that we have, this is the Qiskit library, and the Qiskit AER, that is the simulator, where we will be running our codes currently. We will try to see some real hardware also, but in IBM Qiskit actually now asks for your credit card information when you log into their cloud platform. So we'll try to see that how that can also be harnessed. So or else we will do this the idea of trying to run a real hardware on our code on real hardware from this Jupyter notebooks itself. So the understanding what we are seeing in here, that we are just trying to check Qiskit version and the Qiskit AR version. This is the basic idea. This will be shared with everyone, so you will understand clearly. Now, this is one way of writing the code, and this is the basic superposition code. This might seem somewhat intimidating. Let us go towards the simple part. This is IBM's Quantum Composer. Now, what happens in this understanding and this particular 4 to 5 line code? Same thing is happening, nothing else. There is no change in here. In here, if you see, we are getting a quantum register, a single quantum register, a single classical register. We can change this to 1, 2, or anything else. It will, I think, not run more than 6 or 7 qubits because of limited, you can say, availability in this platform. So till this point, we haven't discussed any gates, any unitary evolution, but I'm just taking some liberty to make you understand that how the superposition and anything else actually works. Right now, if you are able to understand this, if you see this, the probability that we are seeing is 100% for 0, whereas for 1 it is 0. For 0 it is 100%, and for 1 it is 0. Why it is that? Because IBM Qiskit by default takes 0, that is the zero basis state, as the initial, you can say, starting point. If I want this computational basis state to be 100%, I will need to place a NOT gate on this particular qubit, that is the first qubit. Let us try to see this. So as soon as I put a NOT gate on this qubit, that is the Q0, we will be getting 1 with 100% certainty. And this is the state vector. That is, the state vector is also telling us that our state is 0, 1. That is, 1 is present with 100% certainty. And this is the same idea that we saw earlier. Where it was, yeah, this one. That how 0 and 1 are actually, you can say, being shown in here. Now, let us remove this and just continue with the idea of that superposition. So superposition is actually handled, or you can say, implemented using the idea of this Hadamard gate. Right now, we had just seen the basic fundamental idea of what exactly is a superposition, but how to achieve that mathematically achieved through this Hadamard gate. We are just drag and dropping this Hadamard gate, and now you can see this is what we get. We are getting 50% probability of state 0, 50% probability of state 1. Why so? This is right now in superposition. The state vector we are getting, it is 1 by root 2 and 1 by root 2. This is what the same idea that was written in here. Where it is, it was back. I think it was not written somewhere. No worries. I think it is not written in one of the slides. Yeah, this is this. Alpha square and beta square, that is 1 by root 2. When we move towards it, we get this understanding. That is 1 by root 2 and 1 by root. I'm just showing you with respect to reference, but exactly this is not what will be done. So the idea is that as soon as we apply this Hadamard gate, that is a matrix only, and very simple matrix, a 2 cross 2 matrix with all the entries as 1, and the last entry, that is A22, it is -1. We apply this Hadamard to this 0 state, that is 0 qubit. As soon as we multiply that and get our result, it is a simple matrix multiplication. We will be getting a balanced idea of 1 by root 2 and 1 by root 2. Now, right now we are not getting this, you can say, result. We are getting this result in the terms of amplitudes only. If we want a definite state, what we need to do? We need to introduce measurement, and this is where this measurement comes in. And this measurement will be done through which idea? That is, we will be pointing it from the qubit, from the Q0, that is first qubit, towards the first classical bit. Why it is so? Because the answer, it will be coming in classical, you can say, classical reality only. So now if you see the probability, it has changed. The probabilities have changed, and how many shots have been done? 1024 shots, and with that we get 50.488, and for the 0th, and the probability of the second one, that is the state one, is 49.511. And now with definite, you can say, 100% idea, we are 100% deterministic value, we are getting this 0 state as, you can say, all the times. And this is the same idea, that is, if you see in here, we haven't done any measurement in here, so that is why we are just getting the superposition. This is what is being written in here. Every way is good, whether you want open custom way to read it out, whether it is a Qiskit way, and this is pure Qiskit. I prefer personally the this Python way of writing it, because this becomes very natural, very simple. So when we write this QC equals to quantum circuit 1, 1, what this means is that this one is for quantum bit, that is qubit, and this another one is for the classical bit. Then we do H0, that is, we are applying Hadamard to the first qubit, and as soon as we measure it, we will be getting the idea of measuring the qubit 0 into classical bit 0. And how this result can be shown? It can be shown this transpile circuit, and we will be getting a roughly an idea of 0 as 500 times and 1 also as 500 times, and this is what exactly we are getting, 551 or 449. As you run it different times, I think let us run it, we will get different results. 506, 494. We run it another different times. If you reduce these shots, you'll see some more different results, that is 4555 at 3862. Now you see there is a little bit of skewness towards 1. So as soon as we increase the shots, the result will stabilize more. 5078, 4922. And as soon as we go along this, this idea changes. Now, a quick note on how we can see this. It can be done. It can be seen through this MPL, that is the matplotlib library only, and the same circuit that we are seeing in here. This is what we have just built through that drop down. This is the you can say the histogram count of how we can see the distribution that depending on the number of counts. And this is the another idea that Bloch sphere. That is how you can visualize it. So this 0, it is telling us that this is the north pole. That is, this north pole is giving us the 0th state, whereas the complete change of, you can say, if I just change it to another idea, it will be giving me another state. That is one state. Then we get a superposition through the idea of applying Hadamard. So this is a superposition that is pointing towards this X, you can say, direction. And lastly, the idea of this states, the shots. If you see, if we use just one shot, that was asked earlier also, we will be getting a specific one out, single outcome. If we are using 10 shots, we will be getting some, you can say, fair share of 5-5 or 6-4 or anything like that when we run it different times. If you see this, and when we have 1,000 shots, it will be subsiding much more. So the idea of no superposition that can also be quickly seen if we just remove this. If you see this, when we have no superposition, we are getting this 0 state with 100% probability possibility. Why? Because the starting state, as we see IBM Qiskit, is what it is dependent on. It is starting with 0 only. If I just put a negative, you get 100, you can say the state 1 with the 100% possibility. So this is the basic idea around superposition. Let's keep this entanglement and other discussion for tomorrow, because this needs a little bit of understanding of other gates. That is this gate specifically. What is this gate? This is C0, that is control not gate, where we have a controlled qubit and a target qubit, and we are doing the measurement from pertaining to first qubit and the second qubit, and we'll also see the bit ordering because IBM Qiskit actually uses a little endian ordering, so it is a little bit different. In single step, it seems very okay, that that there is no problem, but as soon as we move towards this 2 or more qubits, it becomes somewhat complex. We will have to understand that how this ordering actually creeps up. It becomes somewhat problematic. Okay, so this is what I wanted to like discuss for today. Before phasing out for the closing out the session, I would like you to go through this video particularly, and please come up with the Qiskit involved, you can say, installed on your system through the idea of Anaconda VS Code and all. Because if you are not installing this this Qiskit, you will not be able to run any circuit, because tomorrow we will be doing this side by side, that I am also showing you the code and you are also applying it on your system, so that you get an understanding of how exactly it is done. Because it will not be a kind of a passive learning that we will do it later, we can procrastinate. It will not lead any good results. So yeah, thank you everyone for listening to the being connected for this long. And yeah, I would like to take quick questions till everyone is involved in the attendance and all. Yeah, let me see some questions. So we had seen says okay, high confirmation. Okay, this is from Manisha ma'am. Classical computers use 0 or 1 bit. Fuzzy used to solve the problems of approximation between 0 and 1. And what is difference between fuzzy logic and quantum? Okay, even in fuzzy logic, we have a spectrum of values, whether it is coming from you can say it is between 0 to 1, but the values, the idea is that it is deterministic every time. There is the understanding is that we will be as soon as you just put it in a particular context, it will you will be getting a definite value, and it is not a black box. You are knowing the outcome even before you start. It's like when you toss a coin, you know for sure that either I will get a head or a tail. That is a particular you can understanding that this is done. But in quantum computing, what exactly we are facing is that the idea is that this is a kind of a black box, a kind of a mystery that we are not knowing until and unless we are observing it, or you can say measuring it. So this is where the understanding of whether it is a zeroth order logic, proportional logic, that is first order logic, that is the predicate logic, or fuzzy logic, or any symbolic logic, or any kind of logic, everything in that sense is deterministic right from the start. So this is where the you can say there is a distinction between classical computing methods and any classical computing methods and the idea of quantum computing. Okay, I hope this helps. Next, next, I'm seeing one more question, that is, if a qubit exists in multiple states, Manoj sir has asked this. If a qubit exists in multiple states, why do we measure only one? Sir, we had discussed this, that when the qubit is existing in a particular state, in multiple states, but as soon as we measure it, we are getting a specific you can say answer. We are not like getting every amplitude. This is what I just told a little earlier, that we will be getting a specific amplitude, because now we have observed the system, and this observation is leading to a deterministic answer. Now we are not just in a superposition, in a probabilistic understanding. So this becomes a deterministic idea after measurement. Before measurement, Lakshmi ma'am has asked, before measurement, a qubit can exist in a superposition of 0 and 1, but after measurement, the superposition collapses and we observe only at the 0 or 1. Just like a classical bit, if the final result is always a classical 0 or 1, where does the advantage of quantum computing? Yeah, that's why ma'am, we discussed that it is not just coming from superposition, it is coming from superposition plus interference. So both of them are needed. It is not just the black box is like wielding the power. Again, one more question from the Lakshmi ma'am. What would happen if quantum states had only amplitude but no phase? Ma'am, then that's not like actually you can say an appropriate idea of an amplitude, because sorry, of an you can say a state, because when we have magnitudes as well as phase, then the whole you can say advantage is coming from. Otherwise, it is just a simple vector. So because vector is also having some magnitude and direction, but the phase is all about not just a simple direction. It is about that how constructive interference and destructive interference come together to wield the power of some quantum advantage. Can a global phase ever become a relative phase in a larger quantum? Does it always remain? No. I think let me think about it a little. So this is a good question, I guess. No, a global phase will not, I think, become a relative phase in that sense, because a global phase is all about the idea that how the observability actually that we see, it comes from the idea of how perfectly distinguishable the states are, and this global phase tells us that the states are they are same, they have same physical state. So even if we do measurement, it will not be able to distinguish them. That is a quick idea, that if we have the zero state and the other state is also zero, uh, they are both same thing. But as soon as we write 0 and -0, then there is a change happening. This is where we see the relative phase. So global is will remain like that only until unless we are introducing some phase, you can say the change of phase in through some particular operations. It might change depending on what operations we are actually applying. If global phase cannot be measured, why do we study in quantum mechanics? It is the idea, the global phase, the idea is that even though it is unobservable, but the understanding is that we need to see, we need to compare that one state and how it is faring up with the other state, because in the terms of the understanding of phase, this measurement has a basis, it has a direction every time, and this direction is actually gives us the advantage of the constructive direction, you can say idea, that is we add together this both of the you can say same physical states to get a more profound understanding of how you can say a constructive interference pattern can be done. Yeah, actual source we have discussed, it is superposition plus interference. Why do entangled qubits show perfect correlation in this Bell state? What in the mathematics of quantum state eliminates the possibilities of zero and y? Yeah, ma'am. This particular thing we will be discussing tomorrow. That's the first thing that we'll be discussing. This is the particular thing, so I will not try to answer this right now. Please ping this question again, Lakshmi ma'am, so that we can discuss this in detail. This is very important question, that that how only 0, 0 and 1, 1 are observed, and through 4 different entangled states, the Bell state, sorry, that is how this different you can say configurations are possible. So we'll see that the first thing itself in the tomorrow's session. Next question, is there any? I think we are done for the day. Okay, yeah, there are no more questions. So I hope I was able to provide you the answer that you were intending to ask. So yeah, thank you everyone for connecting. Over to you, Shishmita ma'am.
Yeah, yeah, sure. Thank you so much. We'll meet again by tomorrow at 3 p.m. Thank you. Yeah, so dear faculty members, as today is the day 1 session, so that's the reason you all have received the Zoom and YouTube links to your registered mail ID. From tomorrow, you will be not getting any kind of session links where you have to join from LMS, or you can use the same Zoom link for all the 5 days. Okay. Yeah. So I think we can wind up for the day. Thank you all. Thank you for joining. Thank you, sir.